Greetings and wishes from Rohini College of Engineering and Technology and myself Manoj, Assistant Professor Mechanical. So in this part, we are going to solve the problem on heat transfer through composite plane wall. In the previous session, we have discussed all the fundamentals and basics and the related formulae for solving the problems on heat transfer through a composite wall. A furnace wall is made up of 3 layers of thickness 25 centimeter. Therefore, the thickness is given. First, read the problem completely, 2 or more times to understand. After understanding the problem, we can solve the problem. A furnace wall is made up of 3 layer of thickness, 3 layer. Therefore, I have identified the given problem belongs to the composite plane wall since it has been given as 3 layer. Thus, that 3 layer having the thickness of 25 centimeter, 10 centimeter, and 15 centimeter. That is the first layer having 25 centimeter thickness, that is L1. The thickness is said to be L. Therefore, L1 is equal to 25 centimeter and L2 is equal to 10 centimeter and L3 is equal to 15 centimeter with thermal conductivities of 1.65 and 9.2 respectively. And here it has given us the K1 and K2 values were given. In this problem, the 3 layers, that means they haven't mentioned any kind of material, simply they have given the thermal conductivity of material 2 layers, and the 1 layer the thermal conductivity was not given, right? The inside is exposed to gases at 1250 degrees centigrade. The inside surface, the inside layer, that is we can note at the point T1. This is the inner surface and this is the outer surface. T4, the area near the T4 is said to be a outer surface. Therefore, the inner side is exposed to a gases. As we already studied, any heat transfer through any fluid medium is said to be a convective heat transfer. Since we can understand the given value, the inside is exposed to gases. That means the convective heat transfer taking place initially. Therefore, at initial stage, due to the conduction heat transfer, the heat is transferred from the gases to the surface of the wall. That is 1250 degree. Therefore, it is assumed as TA, where TA and TB be the temperatures of the convections. And T1, T2, T3, T4 are the conduction temperatures. And HA and HP be the heat transfer coefficient at inner and outer surface. Okay, let's continue the problem. The inside is exposed to gases at 1250 degrees centigrade with a convection coefficient of 25 watts per meter square Kelvin. Therefore, at the inner surface, the temperature is 1250 degrees centigrade and the convection coefficient HA is equal to 25 watts per meter square Kelvin. And the inside surface is at 1100 degrees centigrade. How to look at the difference? The inside is exposed to the gases is 1250. The inside surface is at 1100 degree. You have to differentiate these things. The inside is exposed to gases, that is the gas is exposed to the surface of the plane wall, right? Here it has been noted that inside surface, note this point, inside surface, that represents the surface, the area at T1, that is the surface of the inner layer. T4 will be the surface of the outer layer, right? Hence it is given as T1 is equal to 1100 degrees centigrade. The outer surface is exposed to air at 25 degrees C. Outside surface means the T4 is given. Outside surface is exposed to air. There should be different. They haven't given the temperature of the outside surface. They indirectly given the outside surface is exposed to air at 25 degree. They have given the air temperature alone, not the surface temperature. So that's why I'm suggesting you people to understand the problem first before solving. Simply we can write the outside surface that represents the T4. Without reading the problem completely, you cannot write any data or don't try to solve the problem without understanding the problem. The outside surface is exposed to air. The outside surface is exposed to air because the air touches the surface, comes to contact with the outer surface, and the heat is transferred. What is the air temperature? That is only given in the problem as 25 degrees centigrade with the convection coefficient of 12 watts per meter square Kelvin. Therefore, HB value given is 12 watts per meter square Kelvin. Determine, they have asked 3 questions, the unknown thermal conductivity. As I already mentioned, there are 2 thermal conductivities given. That means for layer 1 and layer 2, they have given. For layer 3, we doesn't know the thermal conductivity K value. So therefore, we are going to find the thermal conductivity. We doesn't know what is the unknown thermal conductivity. Here we are going to discuss the same. The second question, the overall heat transfer coefficient, that is U. The heat transfer coefficient is H, and the overall heat transfer coefficient is U. That is the reciprocal of the resistance offered in the layers. Third question, all the surface temperature. In this problem, they have given the temperatures TA, TB, T1. The remaining T2, T3, T4 has not given. Hence, we are going to find these values T2, T3 and T4. Okay, let's start the problem. First, you have to illustrate the diagram as per the problem. Here, it has been shown that 3 layers. I have drawn 3 layers and mentioned the convection taking place here. The convection is considered in this problem. Hence, it has been clearly given. The convective heat transfer coefficient also given. And the inside is exposed to gases. So, due to the presence of fluid, it can be assumed as the convection heat transfer taking place. Temperature. TA will be the temperature at the inside surface, not inside surface, exposed to gases. T1 will be the surface temperature at the inside, and T4 will be the outside surface temperature. And I mentioned the L1, L2, L3, that is the thickness of this layers that is given in the problem in centimeters. You have to convert that centimeter value into meters by dividing with 100. Then we have to draw the thermal network diagram. Thermal network diagram is important to solve the problem easily. Without drawing the thermal network problem, so we cannot solve the problem. Therefore, I am drawing the equivalent thermal network diagram. Here, totally 5 different heat transfers. That means there are 2 convection heat transfer and 3 conduction heat transfer taking place. In case from TA to T1, that is a convective heat transfer. That is the heat is transferred through gases. T1 to T2 is a conductive heat transfer. It's of pure conduction because it is a solid layer. T2 to T3 conduction. T3 to T4 is also a conduction. Then T4 to TB, that is the outside atmosphere, the outside air comes to contact with the surface and the heat transfer taking place. Therefore, the heat transfer through air medium. Air is considered as fluid. Therefore, it is a convection. Right? It is shown that 5 resistance are included in this problem. That is, the resistance offered at the conduction at the inside and the resistance offered in the layer 1, and the resistance offered in the layer 2 is considered as R2, and the layer 3, the resistance offered is R3, and the resistance offered in the conduction outside the surface is said to be T, the resistance value RB, the resistance value RB. Therefore, for convection, the resistance value is RA and RB. For the conduction, the resistance value is R1 plus R1, R2 and R3. Okay, let's go to the solution. Here, the convection is considered. Hence, we are using the Newton's law of cooling. Q is equal to HA into TA minus T1. Here, it is considered for convection only. As you know that where is the region, the convection happens from TA to T1, also T4 to TB. So within this limit, the convection heat transfer taking place. Hence, I am going to find the convection heat transfer. First, I am going to find the convection heat transfer. Therefore, I am taking the first convection between TA and T1. Hence, I have written this Q is equal to H. The suffix A represents the inside and suffix B represents the outside surface. Okay, H into area A into TA minus T1. Here HA value is given. HA value is given in the problem as 25 meter square Kelvin into area. Area is considered. Area is not given, and also there is no values to find the value of A. Hence we are assuming the value of A is equal to 1 meter square. Take A is equal to 1 meter square in case. Therefore the unit may comes as watts per meter square. We have found the value for a unit area, right? 3750. TA and T1 values are given in the problem. TA is 1250 and how to convert it into Kelvin, and the T1 is 1100 degrees centigrade. It has been given here 1100 degrees centigrade. By solving this, you will get 3750 watts per meter square. It is a convective heat transfer. Therefore, we are just going to find the value of K. Our aim is to find the first question they have asked is the unknown thermal conductivity, right? Then heat flow Q is equal to the general formula overall temperature difference to the resistance, summation of all the resistance, that is the R total. Here delta T is nothing but the temperature difference, the initial and final temperature, overall temperature, that is TA minus TB. And the R value, for the R value, we know that for the convection heat transfer, for considering the convection heat transfer, the R value is equal to 1 by HA. Considering the conduction, the resistance offered R is equal to L by Ka. Therefore, we have to understand the first resistance is a convection resistance. Therefore, the value is 1 by HA. So, preferably small h is used. Plus, what is the resistance value for conduction? L by K. Here I am differentiating because we are having three different layers. I am differentiating with the numbers in the suffix L1, K1A for the first layer. Because area we are considering as 1 meter square. Therefore, area is same for all the layers. And plus the second layer it is a conduction. Therefore, L2 by K2A. And the third layer is also a conduction. Therefore, L3 by K3A plus the outer surface, the convection happens. Therefore, 1 by HB. HB represents the outer surface. HB into A. Here, as I mentioned, delta T is TA minus TB. I have included both the delta T value and R value here. TA is given 1523 Kelvin minus TB is 25 degree is given in the problem. So we can take 298 divided by 1 by HA. HA value is given 25 into A. Area is considered as 1 meter square. So no need to bother about it. There is no option to find the value of A. Hence we have assumed the value of area is 1 meter square. For a per meter square alone, we are finding the answers. That's why here we put the Q by A. The reason is we have taken the A as common. Okay, we are taking this denominator 1 by A as common, right? Okay, then by cross multiplying this, you will get Q by A is equal to these values 1 by 25 plus L1. L1 is given in the problem 0.25 meter divided by K1. Divided by K1. K1 value is 1.65 watts per meter Kelvin plus L2. L2 value is given 0.1 meter divided by K2. Here we have considered the K2 value is unknown. Since the furnace wall is made up of 3 layer of thickness, all the 3 as given, with thermal conductivities of 1.65 and 9.2 watts per meter Kelvin respectively. That means it has been given the first layer, the initial layer and the final layer. The thermal conductivities has given for the initial layer and the final layer. Right? Hence, we are considering or we are assuming the K2 value is unknown. Therefore, our aim is to find the value of K2. Therefore, K2 is equal to K2 we are going to find. Here it is wrongly mentioned. There is a K3. K3 is equal to 9.2. Then plus L3 by K3A. L3 value 0.15 meter divided by K3 is 9.2 watts per meter Kelvin. From this, Q value we have found in the previous step, that is Q by A. Q value we have found in the previous step. Therefore, unknown value is only K. K will be the K2 will be the unknown. By solving all those things in this equation, we will get K2 is equal to 2.816 watts per meter Kelvin. Then overall thermal resistance, that is, we are going to find the total resistance value, that is 0.3267 watts per meter square. So by solving the denominator, because since for finding the value of R, we need all the thermal conductivities. So in the previous step alone, we have found the thermal conductivity of the material second layer. So hence after finding the thermal conductivity of the second layer, just we find the value of total resistance 0.3267 watts per meter square. Then the second question we have to find is U, the overall heat transfer coefficient, that is equal to the reciprocal of the resistance, total resistance offered, is equal to 1 by 0.3267. The total resistance is we have found in the previous step, right? Here in the last step, R total has been found. By applying this, we will get the overall heat transfer coefficient U is equal to 3.06 watts per meter square Kelvin. Okay, two questions we have found. The unknown thermal conductivity and the overall heat transfer coefficient both are found. The third question, all the surface temperature. Here the surface temperature T1 is known, is directly given in the problem as 1100 degrees centigrade. But in case we don't know, we doesn't know the value of T2, T3 and T4. Here our aim is to find the value of T2, T3 and T4. For that, we are dividing the thermal networks, that is Q, the heat flow Q is equal to TA minus T1 divided by RA, that represents the convection heat transfer Q. Therefore Q for the next resistance, Q is equal to T1 minus T2 by R1. And for the second layer, that is T2 minus T3 by R2. Is for the last layer, third layer, T3 minus T4 divided by R3. And for the convection, T4 minus TB divided by RB. This is very simple to understand. Look at the thermal network diagram. So in as we know that the Q formula is given as delta T divided by R. Delta T is the temperature difference between, so there is a temperature difference in the layer, and RB the resistance. So considering the convection, first convection, here the resistance is considered as RA. Therefore the delta T is TA and T1. This is the temperature difference of the convection heat transfer. Hence the temperature difference delta T is equal to TA minus T1 divided by the resistance here is RA. Then for the conduction, for the three layer 1, 2, 3, the value of R is R1, R2 and R3. And for the convection it is RB. Therefore the temperature difference in the first layer is between T1 minus T2 divided by what is the R value? R1 here. And the next set T2 minus T3 divided by R2. Then T3 minus T4 divided by R3. Okay. After that convection T4 minus TB divided by RB. So this is how we have written this equation. And from this you have to take the possible equation to find the value of the temperatures, right? Consider the second temperature, right? Q is equal to T1 minus T2 by R1. So before that you have to find the value of R1. We know that R formula, R is equal to 1 by HA for convection and 1 L by Ka for conduction. Here in the first one is convection and second one is conduction, third is conduction, this is also conduction, and the fifth is a convection. Okay, therefore we have taken this value. Here it is a conduction heat transfer. Q is equal to T1 minus T2 by R1. Therefore R1 is equal to L by Ka. A is taken as 1 meter square. So have to substitute the value of L and K. By solving this you will get the R value. Then by substituting the R value in this equation, here the Q value is already we found in the previous steps, and T1 value is given in the problem as 1373 Kelvin, and T1 is and T2 is unknown. That's why we are going to find, divided by the R1 value we found in the previous step. Therefore T2 is the unknown value. By solving all those things we will get the value of T2 is equal to 804.8 Kelvin. Then take the next set of value. Q is equal to T2 minus T3 divided by R2. Here we are going to find the value of R2. R2 is equal to L2, that is the thickness of the layer 2 divided by the thermal conductivity of layer 2, because R2 will be the resistance offered in the layer 2. Okay. By finding this you can find the value of R2, and the T2 value we have found in the just previous step, 804.8 minus T3 value is unknown here. Remaining all those values are known. By solving this you will get the value of T3 is equal to 671.45 Kelvin. Then taking the next one, T3 minus T4, because we have to find the value of T2, T3 and T4. So T3 minus T4 by R3. R3 is the resistance offered by the layer 3. Hence the formula is L3 by K3 A3. A3, A is 1 meter square, we have taken common. Therefore L3 by K3 is known, is given in the problem. From this you can find the value of R3, and here the T3 values we found in the previous step, 671.45. The T4 value is unknown in this step. Therefore by solving this you will get the T4 value as 610.30 Kelvin. You have to note this point, the temperature should be keeps on decreasing according to the Fourier's law of conduction. The heat should be transferred from one layer to other. The decrement of the temperature will be noted. So look at the initial temperature is 1373, the initial surface temperature T1, and T2 is 804, the decrement, and after that 671, after that 610, the decrement is come. Therefore our doing is right. Suppose if you want to cross check whether our values are right or not, consider the last one. Q is equal to T4 minus TB divided by RB. That is equal to RB value. RB formula is 1 by HB into A. HB value is given in the problem. So therefore you can find the value of RB, where T4 is found in the last step. T4 is equal to 610.30, where the TB, keeping the TB as unknown, right? Therefore by solving all those things, just try to find the value of TB, which would be correlated with the given data. The TB value 25 degrees centigrade, it should be correlated. If it is not matching, at least approximately it would be matching. Otherwise if not, your answer will be wrong. Hence here we have given the conclusions. The unknown thermal conductivity is the K2 middle layer, we found 2.816 watts per meter Kelvin. The overall heat transfer coefficient capital U is equal to 3.06 watts per meter square Kelvin, and all the surface temperatures, the the T1 value is given in the problem directly. Hence, we found the value of T2 as 804.8 Kelvin and T3 671.45 Kelvin and T4 the surface the outside surface temperature T4 is equal to 610.3 Kelvin. Thank you.